Okay, this next part is very, very important. It's what do you do to find the derivative of an exponential function if it's not e? So we know the derivative of e to the x is e to the x, but what's the derivative, for instance, of 2 to the x? And the answer is it's kind of the same, but there's a little bit of a tweak. So what's the derivative of 2 to the x? It would be 2 to the x, but you have to remember the change of base formula. The change of base formula you probably learned in college algebra. And the idea was if your base is not an e, you can make it an e. And that's what they did in the back of this, in the auxiliary section of this book. If you want to see the proof of the derivative of a to the x, you could use the change of base formula to get it in terms of e, and then we know the derivative of e to the x is e to the x. Then you would change it back at the end, find your derivative, change it back, and you could get this formula. Again, I'm not asking you to memorize the formula. All I'm asking you to do is be able to do it. So what's the derivative of any number raised to the x? It's that exact same thing, copy and paste. So it's still that number raised to the x, but you have to remember this new part, which is multiplying times the natural log of the base. So let's look at the first example here. Same thing, number 2 here is just the chain rule. Just copy and paste, multiply times the derivative of the numerator, but just add that new part, multiply times the natural log of the base. So if the base is at e, we have to multiply times the natural log of the base. So here we have, if you notice, our a to the x on this one, a is equal to 3. So if we want to find the derivative of this, f prime of x, we do exactly as we did before, copy and paste. We have to find the derivative of the top. Well, it's just x. The derivative of x is 1, so we don't need to worry about that. But we do need to multiply it times the natural log of the base. So how would I write this? I'd probably write it as the natural log of 3 times 3 to the x. I don't know. It's up to you. I honestly, that 3 to the x times the natural log of 3, that works for me. I'm perfectly happy with that as well. Not too much work to show on that one. That's what the answer is. Let's go on and make it a little more complicated. Let's look at example B here. It says, what is the derivative of 5 times 1/2 to the x? I want to tell you what I see a lot on the test when students are panicking. I see a lot of students say this is the same thing as 5/2 to the x. That is absolutely 100% mathematically incorrect. Anytime you have something raised to a power, you can't just sit there and say, oh, let me bring the 5 inside. If it's raised to a power, you cannot distribute the 5 to the inside of that. So that's absolutely mathematically false. Please, please, please don't do that. Let's go ahead and erase that. This is a constant multiple. So remember, when you're finding the derivative of any exponential function, to find the derivative, you copy and paste. So this would be 5 times 1/2 raised to the x. That's our copying and pasting, right? Now we need to worry about multiplying times the derivative of the exponent. Well, the exponent is just x, and the derivative of x is just 1, so we don't have a chain rule thing that we have to worry here. But we most definitely need to worry about multiplying times the natural log of the base, because the base is an e. So that's the part that's most often forgotten, is multiplying by the natural log of the base. So the final answer would be 5 times 1/2 to the x times the natural log of 1/2. I don't really care which order you write that in, but you could write that in a different order if you prefer. Here's a good one. This would be a good test question here. C. What's the derivative of 2 raised to the x squared plus 1? Great test question here. Okay. So what do you do to find the derivative of an exponential function? Again, it's not going to change. Copy and paste. So this would be 2 to the x squared plus 1. Now we have 2 things that we need to worry about, though. We do need to find the derivative of the exponent, just like we did in the previous section, but we also need to compensate for the base. So there's 3 pieces to this. Copy and paste, derivative of the exponent, and then the natural log of the base. Copy and paste, derivative of the exponent, and then the natural log of the base. So what's the derivative of x squared plus 1? It's simply 2x, well 2x plus 0, which is 2x. So putting that all together, let's just kind of clean it up. What do we have? We have a 2x, we have a natural log of 2, and then we have a 2 raised to the x squared plus 1. And there it is. In either order, again, this is multiplication. Multiplication is commutative, so it doesn't matter which order you have those three things in. You just need those three things there. Let's move on to D. D is f of x equals 1/3 to the 3 minus x. What do we do for the derivative of an exponential function? Again, remember there's three parts to the derivative of an exponential function. We copy and paste 1/3 to the 3 minus x. We do the derivative of the exponent, so we need to do the 3 minus x, the derivative of that. And then we have to do the natural log of the base. In this case, the natural log of 1/3. Copy and paste, derivative of the exponent, natural log of the base. What's the derivative of 3 minus x? Well, the derivative of 3 is 0. The derivative of negative x would be a negative 1. Putting this all together then, what would I have? Well, I'd have a negative. I'm not going to write the 1 because that's not simplified. I'd have the natural log of 1/3. And then I'd also have a 1/3 raised to the 3 minus x. Again, a good test problem there for you where you have a different base and you have to use the chain rule. Okay, why do we care about this? Exponential functions happen all the time in the real world. Heck, COVID-19, which is happening right now as I'm recording this video, that is a function that is exponential growth. That's what they were freaking out about. So exponential growth happens all the time in the real world. You could have growth, which is what happens with COVID, or you could have decay, which is what happens, for instance, if you've ever heard of radioactive decay or radioactive and carbon dating. The way they do that is through decay, and they use something called the half-life. Half-life is how long does it take for half of the amount of carbon to disappear from this instance. So let's give this a read right here. It says radioactive carbon isotopes have a half-life of 5,715 years. An object contains 1 gram of the isotopes. The amount in grams that will be present after t years is A equals 1/2. Again, that 1/2 is coming from the half-life. And then it's t over 5715. Notice that's the half-life of this radioactive carbon isotope. So it says, at what rate is the amount changing when t equals 10,000 years? So again, they want to know the rate of change at a specific moment. And a rate of change at a specific moment means that we are finding the derivative at that moment. Okay, so what do we need to plug in? We need to plug in 10,000. We need to find the derivative and plug in 10,000. So we're going to find the derivative of A with respect to t at t equals 10,000. Okay, and this isn't like the 2010 you plug in t equals 10. This is actually t years, so we do need to plug in 10,000. That's a long time, but we're going to see how much of it is left after 10,000 years. Let's think about our units right here. What is A measured in? A is grams. What's t measured in here? T is measured in years. And remember, why do we care about that? Because we're going to always have to label our answer. This is going to be grams per year. This is decay, so hopefully, without even thinking about it too much, without even doing the math, just thinking about it, I should say, I should have a negative number here, right? Because the amount of this radioactive carbon isotope should be decaying, should be getting smaller and smaller as time goes on. Okay, so what are we going to do? We're going to find the derivative. We're finding the derivative of 1/2 t to the 1/2 to the t over 5715. That is an exponential function. And remember, with exponential functions, to find the derivative, we have three parts. We copy and paste, so we have 1/2 t over 5715. We have to do the derivative of the numerator, so t over 5715. We have to do the derivative of that. And then we have to do the natural log of the base. So in this case, that's the natural log of 1/2. Okay, let's continue on. So what we really cared about was this at 10,000 years. So now we're going to plug in 10,000 for t. So I'd have 1/2 times, or raised to the 10,000 divided by 5,715. times, oops, sorry, I forgot to evaluate that derivative. The derivative of t over 5715 would be 1 over 5715, because the derivative of t is just 1, and that's just a constant multiple. So I'm going to multiply this times 1 over 5715. Then I'm also going to multiply that times the natural log of 1/2. Be very, very careful putting this into your calculator. Let's see what you get. Putting it into my calculator very, very carefully. Here's what I'm getting. We're going to have to look at some decimal point value here. Okay, so what I got was a negative 0.0000, about 36. How about that right there? So what's happening? That negative value right here means that it's decreasing at a rate of negative 0.000036 grams per year. So very, 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 very little of this carbon isotope, radioactive carbon isotope, is disappearing every single year. Again, that's not how much is left. That has nothing to do with how much is left. That's how much is it changing. So from 10,000 years to 10,001 years, whatever the amount of grams that was left of it, there would be 0.000036 grams less in 10,001 years after that asymptote happens. So that's what we're talking about there. Again, rate of change derivative at that point. Okay? If you did have a calculator, by the way, I just wanted to note this. You might have seen something like negative 3.6 times 10 to the negative 5th, or e negative 5. If you saw something like that, negative 3.6, and then it's times 10 to the negative 5th, what's that means? That negative power there, that negative power just means move the decimal to the left that many times. So I moved the decimal left 5 times. My calculator actually gave me the decimal version because the way that I put it in. But if you did see that scientific notation, don't freak out. The negative power just means move the decimal left. If it's a positive power, that just means move the decimal right.